The quantum elevator. When your energy floor rises, going up, see what happens when we give a quantum particle an unexpected lift in its infinite square well home. So in this problem, 11.26, we're tasked with a particle starts out at time t equals 0 in the nth state of an infinite square well. Now the quote floor of the well rises temporarily, maybe water leaks in and then drains out. So sometimes this is called the Schrödinger bathtub as well. So that the potential inside is uniform but time dependent. So V naught T with V naught T at 0 equals V naught T at the end equals 0. Okay, so instead of rising up, at both the time endpoints were 0. And then right in the middle, with time being what it is, it rises up. So then part A, solve the exact C sub m t using equation 11.116 and show that the wave function changes phase, but no transitions occur. Interesting. Find that the phase change phi at t in terms of the function v of t. Okay, and then B, analyze the same problem in the first order perturbation theory and compare your answers. So why do we care? Well, now we're dealing with a multi-level system, hence the nth state instead of a two-level system where we're comparing two energy levels. And what this leads to is phase changes without transition. So that's pretty cool. Now, the challenge for you is how do we interpret these results? Given that the floor rises for some time, but there's no transition, aren't we increasing the energy level? Let's see what happens. That being said, the PDF is available, although most of it is in the video, so you're not going to miss too much. But if you want it, just comment and I'll send you the Patreon link. If not, you can access it in the link in the description. Either way, you'll be good to go. But before we dive into today's topic, you should know that my goal is to break down complex physics concepts using exercises from top books. If that sounds like something you'd be interested in, hit the subscribe button and join us in exploring the universe. All right, so stop one. First, we have to get our game plan down and see what everything is doing. So for part A, for a multi-level system, we see that C dot M is equal to negative IH bar with sigma over N, okay? But we have the matrix element here, which this is the equation here, and then we have the, for the coefficient, time-dependent coefficient, but we see that we have it between two different states, but they could be in any different states, not necessarily one above, one below, but arbitrary level. Okay, and as expected, this matrix element from 111.117 is pretty much what you would think it would be for this setup. Okay, so then we have the perturbed Hamiltonian here between the two states of interest. Again, they don't need to be neighboring. Okay, and then we see that our perturbation here does not change in the kinetic energy term, but just the potential term, because we have something here with respect to time. Okay, but at the endpoints, we're fine. Now, what we have to realize here is that because this is an inner product, right, and this potential is only time dependent, we could take this outside because the inner product is with respect to the spatial coordinates, not time. Okay, so we took that outside. Now we see that we just have the inner product of one wave function with itself. Of course, we see this exponential tagging along with the energy states, pretty much as expected, though. We saw that even happening back in chapter 2. But because the inner product here is of two different states, m and n, we know that being a complete set, they need to be orthonormal, so that's going to go to the Dirac delta. So that's Dirac m and n. Note that we're summing over all n indices. So if we want to find out what's going on, we can only have one state here because it collapses all to the m state. So Cn here goes to Cm. And then this n up here goes to C or EM. So we put all of it indexed to M, and now we can see that this cleans up relatively fast. EM minus EM brings us to 0, so that exponential goes to 1. We see that here. Now we just simplify it down to this expression here. But let's remember that this was all equal to the time derivative of Cm. And so we just recap that here, show that it's the time derivative, And this looks like a separable differential equation. So multiply the dt element over here, divide the cm element over here, and now you have an integrable equation. Again, not too bad, pretty much expected a differential equation that's nice to see compared to the second order stuff we've been dealing with in terms of these coefficients, so not too bad. Now what we see is that integrating both sides, this constants can come outside, and we have an expression that looks awfully familiar. The integral of v0 t with dt, and then over here we have the derivative over itself. I think you know what that's going to lead to. So simplifying this, we get to ln of cm, the constants out front. And now what we do to keep it in line with trying to set everything up in the t coordinate, we just put primes here and then we integrate from 0 to t typically. So, but we see here that upon integrating, we get a constant here, so we just put that over there and we're good to go. Now, to get rid of the ln, we take the e to the both sides, so exponentiate both sides. And you see you get e raised to this thing. We've seen that for several chapters now, so it doesn't look crazy. But of course, splitting this up, when you have an addition inside the exponential is the same as multiplying by the same base. But we know that this e to a constant is just another constant. So we call that cm at t equals 0. Makes sense. And so clearly, if we let phi of t be what's inside the exponential, okay, uh, regardless or without the I, of course. I don't know what I'm trying to say. But without the I, we let phi there. Then we can see we get a complex exponential of this form. And that's pretty cool. So, getting to this process wasn't too bad as compared to the time-dependent perturbation theory with those coefficients A and B. But that was for a two-level system. Now this is an in-level system or multi-level system. So what do you think about this? Drop a comment below with your thoughts. I love hearing your interpretations and questions. That being said, we still have to find the probability. So what is the probability here? Well, that's just the coefficient squared and the magnitude, but that means the conjugate times itself. So let's take this piece by piece because this does get a little annoying. So conjugate of the coefficient at t equals 0 term, flip the sign on the I, leave the other two alone. Reorganizing, thanks to multiplication, we see that the negative exponential and the positive exponential, they'll go to 0. But since we have c star m, cm, that could just go back to the magnitude. And now we see that we have E0, which is just 1, so we retain the magnitude of the original coefficient. That's pretty darn cool. And so what we want to say about this is that since the probability is exactly the same as in the initial state, there are no transitions. Because remember, the floor started rising up after t equals 0. Okay? But there is a phase change. And this, kind of makes sense if we run around it in a different point of view where if we know that eventually at t equals 0 and at some later time, capital T, they both go down, the instantaneous eigenstates all go up, right? So all the energy levels go up simultaneously, so the difference between them don't change. And that's where we're thinking that that's going to cancel out but lead to a phase change. So that's pretty cool. So that brings us to the conclusion of stop 1 in part A, and now we can move to stop 2, where we're trying to compare two old results. So looking through the first order lens, we see here that from equation 11.18, going back to that again, we see Cn, capital N of t for some arbitrary nth state is approximated with 1, since we know we are in that nth state early, minus this correction factor here, which is the inner product of n and n. Okay, so once again, we see psi n with the perturbation here. And we'll just run it through the same scenario that we did in part A, get that potential out and simplify. So putting in the time-dependent potential, get that outside since our inner product has to deal with spatial variables. Now we see that we're normalized, so orthonormal, same index, so we go to 1. And now we're just left with this. But note that this negative I, h bar, and all this integral, that's going to go to negative phi. So the negative and negative will cancel, or you can just substitute out the negative altogether. Either way, you get 1 plus I phi of t. Okay, that's pretty weird considering that we just had an exponential, but we got to remember that this is the first order lens. Okay, so comparing that with the other equation for the M state, which was given by 119, we see that we can approximate this other M state via this integral here with the new matrix element. Plug it in, run it through the same gauntlet. The matrix element now has the differences of the two states because the exponential of E capital N minus En just gives you 1. Now we have the difference of the two state energies. So plugging this in, whittling it down, time dependent, we can pull that outside and we'll see we get a delta again. Okay, so time, the potential outside, difference of two states in the inner product, we get a delta. And then once again, we see that this goes to 0 because M is not equal to N. So that delta goes to 0. Well, that solves that. That makes our life easy. So the two coefficients here that we have are Cn for the in state itself is equal to 1 plus I phi of t, but Cm at some other state is equal to 0. Once again, confirming that we don't transition, okay? So that is very helpful. And so what we just did was find the coefficients for the time dependence that we needed, perfectly fine, but in comparing with the exact result from 1.8, we saw that that was just equal to e to the I phi t, where all we saw was a phase change. Again, we verified that in part A, but with the Cm being 0, these are consistent with the first order because you can break the exponential out into a series approximation to the first order, with 1 being the 0th, and you see you get the same result. That is great consistency within the theory, and that's what we love to see. That being said, that was a fun video. Kind of weird out there, and I'm kind of surprised they didn't put that as more of an emphasis in the section itself. But I can see why it would be put into the extras because it is a little bit more to deal with, and the time that you need to just get the concepts right. I can see why. That being said, I believe Shankar has a lot in his book about this stuff because, quite frankly, you're not going to look at two different states that are next to each other that often, according to the paper he wrote. But we can see that for generalizing this to any multiple states, that's or multiple level state, then this is very, very useful. So if this video got you thinking, imagine what's coming next. Subscribe and join our community for weekly insights into the world of physics. There's so much more to uncover, and I'd love to have you along for the journey. I just want to take a moment as well to thank my incredible Patreon supporters. Your support is truly the backbone of this channel. It's because of you that I am able to create these videos and diving deep into the fascinating world of physics. Your contributions make a real difference in helping me bring these concepts to life, and I'm so grateful for each of you for believing in this journey. And if anyone else is interested in supporting the channel and joining our Patreon community, you can check out the link in the description below. Together we can keep exploring the wonders of science and discovering even more amazing things. As always, thank you for watching, and until next time, stay curious.